I'm going to talk about area under curve, and we're going to use integration later on to find area under a curve. Okay, so let us take a very simple example, something that you already know. Suppose let me draw a graph. Okay, a simple graph of y is equal to 2x plus 1. Say this is your graph of y is equal to 2x plus 1. Okay, so this is your line, straight line, y is equal to 2x plus 1. Okay, so this point is obviously the y-intercept, which is 1. And let me take a point here, 5, comma 11. So when x is 5, y is 11. And we want to find the area under this curve. That means we want to find this area. So let me shade this. We want to find this area, which is the area of a trapezium. Okay, you may know or may not know the area of a trapezium. So this is 5 and this is say 11. Okay, so the question is we want to find the area, and this concept of area under a curve has got wide application. So let's start with a very simple example. So what I'm going to do is I'm going to split this into a triangle and a rectangle. Okay, so if you split this like this much height, this height is 1. I hope you can see that. This is 1, this is also 1, and this width is 5. So this is also 5, and we know this height is 11, so this would be 10. Okay, so the area, without using calculus, area would be area of the rectangle, which is 5 times 1, 5 times 1. Let me write it properly. This is area of a rectangle, which is base times height. Base times height is plus area of a rectangle, which is half, times base, which is 5, times 10, which is the height. So which is 5 plus, this is half of 50, which is 25. So the area is 25 units squared. So I'm not writing the units. So area is 25. Okay. The unit is, of course, unit squared, whatever that unit is. Now, how will we do this using calculus? Now, I'll give you an idea of calculus so that you understand how can we define this area using calculus. So what do mathematicians think? Because people think in different ways. So one way of finding is what we saw now. Now, yeah, let me keep this. Suppose imagine, you can imagine, let me take a very infinitesimally small rectangle. This is an infinitesimally small rectangle. Okay, so the width here, this is your x-axis and this is your y-axis. So this, your width here is dx, which is infinitesimally thin, and your height is y. Okay, so the area of this, you can say area of this, you can say slit, area of one, I'll call this slit. Slit is a small, infinitesimally small rectangle. Would be base times height, which is dx times y. Dx times y, or we can say this is y times dx. Okay, now the idea should be, the concept is this simple. So what I'm saying is, if you want to find the area of this trapezium, it is, if you have infinitesimally small slits like this, so you have an infinitesimally small slit here. Okay, you got an infinitesimally small slit here. Imagine if you can add all these infinitesimally small rectangles. If you add all these infinitesimally small rectangles, that would be equal to the area under the curve. Is it clear? So what I'm saying is, this is an infinitesimally small rectangle, which has, of course, dx. The width is infinitesimally thin, and your height is going to change. So this is your y at this point, this is your y at this point. So if this width is infinitesimally thin, your height is going to change, and if you add all these rectangles, you'll get the area under the curve. So that's where indefinite integration comes in place. So area is the best difficult notation. Area of this same thing can also be found by integrating all the rectangles between 0 to phi. So this is how you write integration, definite integration from 0 to phi of y dx, where your y is going to be your height. Y is your height, which is going to change, and dx is the width, which is constant, which is infinitesimally thin. Okay, and when you say integration, you're adding. This notation means it is the addition of all infinitesimally small rectangles from 0 to phi. And how do you define each of the rectangle? The width of each of the rectangle is dx, which is an infinitesimally small width, and your y is going to change. Okay, so this is what you do. So this is integration of 0 to phi, definite integration from 0 to phi of y. What is y? Y you can write in terms of x, which is 2x plus 1 dx. 2x plus 1 dx. So yeah, what we do is you integrate, as you already know, you can integrate each of them individually. So this is integration, let me write again, 0 to phi of 2x to the power 1 plus 1x to the power 0 dx. Okay, so this is, you integrate this, so this is 2x squared over 2, 2x squared over 2 plus 1x to the power 1 over 1, and this is called the limits of integration, 0 to phi. Okay, you may not understand exactly what I'm doing, so let us simplify this. So this 2 and this 2 gets cancelled. This is x squared plus x from 0 to phi. Okay, so now what you do is you substitute upper limit in this form, and then you take away by substituting the lower limit. So this is called the upper limit. I'll write up, upper, ul, not p, upper. This is called the upper limit, and this is called the lower limit. So you substitute this back in this equation, then take away by substituting this in this equation. So let me explain that. This means this is phi squared. So let me put this in the bracket. Phi squared plus phi minus you have to put the lower limit, so that is 0 squared plus 0. Okay, so this is 25 plus phi is 25 plus phi is 30. Okay, am I doing something wrong here? Oh, this should be 30. So I made a mistake here. I was wondering what was I doing wrong. This is 25 plus phi is not 25. This is 30. Okay, so this is my mistake. Okay, so this is 25 plus phi is 30. 30 take away 0, which is 30 units. Okay, I'll show you how you can do this on a calculator. A calculator will do definite integration for you. So let me go to your graph menu. I'll go very slowly and type in the function, which is 2x plus 1. Okay, and then graph it. Okay, and the only thing that you have to do is you have to have your scale like this. Okay, which is called the initial scale in F1. What I'm going to show will work only when you have scale or initial scale, and then you draw it. So this is a graph. Okay, and then you press G-solve, which is F5, and then you press F6, and then you press F3, which is integration dx. Okay, now this is called, the calculator will say what's your lower limit. So you can see lower there, and then you have to press execute. That means we are saying my lower limit is x is 0, so you press execute. Now it's asking me what's your upper limit. So I want to scroll. Can you see this is going up in 0.1? So I'll go up to phi. It keeps scrolling till you reach phi on x value. So this is 4.5, 4.7, 4.8, 4.9, and when x is 5, y is 11, and then you execute. Can you see what it has done? The answer is the lower limit is 0, upper limit is 5. It has added up all the infinitesimally small rectangles from 0 to 5, and the area is 30. So both we saw the area is 30. So let me take one more example. Suppose the question is, let me draw a graph. Okay, so the question is, you have a parabola. So let me draw a parabola. Hopefully I can draw a parabola. Okay, so this is y is equal to, say, y is equal to x squared plus 1. This is x squared plus 2. Let me take x squared plus 2. This is 2. Okay, and we want to find the area when x, suppose this is, let me draw a dotted line here. Say this is 2 on the x-axis. This is 0, this is 0, and this is 2. So when x is 2, this point would be 2 comma 6. So 2 squared is 4, 4 plus 2 is 6. We want to find this area. Okay, so let's do, let me change this. Let me change find from 1 to 2. Suppose we want to find this area. When x is 1, so this is 1. So this point is 1 comma 3, am I right? 1 comma 3, and we want to find this area. Okay, we want to find this area under the curve. Okay, so let me shade this. Okay, here the problem is you can't use any other method other than calculus. So here area would be the definite integration from 1 to 2 of x squared plus 2 dx. The concept is the same, the idea is the same. What we are doing is you're taking an infinitesimally thin rectangle. Imagine this infinitesimally thin rectangle where your width is dx and your height is y. Okay, so area, what we are saying is area would be the integration of between 1 to 2 of y dx, where your y is your height and your dx is your width, and in place of y I have put the function which is x squared plus 2. So your area using integration would be integrating x squared, this is 1 to 2, sorry, 1 to 2. Okay, so integrating x squared, you'll have x cubed over 3 plus integration of 2 is 2x. And you don't have to put the constant of integration. Okay, that's one thing that I forgot to tell you. When you're having definite integration, the constant will get cancelled. Okay, so let me put the constant. Suppose even if you put the constant, suppose the constant of integration is c, it will get cancelled. Okay, so what I say is area is you have to substitute the upper limit and then take away by substituting the lower limit. So area would be, let us substitute 2 here, so that is 2 cubed divided by 3 plus 2 times 2 plus c, take away, I'm going to put the lower limit here, so that is 1 cubed divided by 3 plus 2 times 1 plus c. So this is 8 cubed, 2 cubed, which is 8 over 3 plus 4 plus c, minus this is 1/3 plus 2 minus c. Can you see the constant of integration gets cancelled in definite integration? So this is, let us simplify this. So this is 8 over 3 minus 1 over 3 and plus 4 plus 2. Hopefully I'm not doing any mistakes. We'll confirm this on a calculator. So this is 7/3 plus 6. Okay, 7/3 is 2, 3 goes in, so 3 goes in 7 twice, so this is 2 1/3 plus 6. So the ultimate answer should be 8 1/3. The area should be 8 1/3 exactly. So let's check that. So let us type in the equation x squared plus 2. So this is x squared plus 2, and draw it. So this is your graph, GSOL f6 integration dx. So your lower limit is 1. So keep scrolling to 1. So this is your lower limit, so you go execute. Okay, so it has drawn a line, and now it's asking you what's your upper limit. So my upper limit is 2. And press execute. 4 1/3. Okay, I've done some mistake here. So let's check. Okay, what's the mistake here? Okay, so this is 2 cube. Okay, is 8. Oh yeah, gotcha. It's always good to check my answer. This is -2. Okay, this should be -2. So this is -2. This is -2. So this is +2. This is +2. And this is also +2. Okay, and finally I can confirm my answer. This is 4. So this is 4 1/3. So let's check it. This is 4 1/3. The area between 1 and 2 is 4 1/3.